Hi. There are four features of an NMR spectrum that are very important to be able to interpret it and to predict or propose a structure for it. They are the number of signals, the integrals, the splitting, and the chemical shift. I talked about figuring out the number of signals and the integrals in a previous video, and here I want to talk about splitting and chemical shift. If we look at an NMR spectrum that we are going to analyze a bit later, what would I say about this particular spectrum? Well, first of all, I would notice that the scale is from 0 to 1.5 ppm, so this is ppm. Normally it goes to 10, but since all of the signals occur below 1.5, they zoomed in on this area. And remember what we talked about last video? These are signals. One signal, two signals, three signals. But let's take a look at this particular signal in the middle. This is one signal. This is my terminology, or the way I prefer to call these little lines. It's one signal, but it's split into 5 peaks. And we are going to talk about splitting. Split into 5. So the individual humps I'll call peaks, the grouping I'll call a signal, and actually we're going to call this a, some people say quintet, I'm going to call this a pentet for 5. Okay. And since we're going to talk about splitting right away, this is a triplet. Do you see how it's 3? Or in literature you'll just see it as a T. This maybe as a P. Oh my goodness. This is 6. Normally, a lot of times you're not going to get up to 6, 7, and 8. We'll call this a sextet. I can't use S because S is a singlet. D is a doublet. T is a triplet. Q is a quartet. 5 is a pentet. 6 is sextet. And so forth. Okay. We'll take a look at 2 examples in this video. But where does that come from? Why was my signal split? Okay, let's take a look at a molecule, and I'll draw out all the hydrogens. I want to do this properly. Okay. We'll put 3 hydrogens here. And 1 hydrogen here for sure. And I'm going to put a chlorine here. Does that satisfy the octet for all carbons and oxygens? I think so. Okay. Let us label, like we did in the last video, the signals. Okay? So these guys we're going to call proton A. And I'll use lowercase this time. This one right here is proton B. These two are equivalent. Remember the term chemically equivalent or magnetically equivalent? Same difference. Means the same thing. Oh, and this should be C. When studying NMR, one way to get really good at proposing a structure is to work backwards. What if we have a structure? Would you be able to predict what the NMR would look like, the NMR spectrum? And this is HD. Okay. Split. Because it looks like we have a signal. Let's say we have a signal that looks like this. Okay. Remember, it's really a hill. There's some space underneath the line, underneath the trace. But I'm just going to write it as a line. But sometimes that signal, that same signal, can appear like a doublet. Okay? Or it could appear like what's called a triplet. And yeah, I'm purposefully making the heights as such, equal heights for the doublet. That middle peak is twice as high as the 2 smaller peaks, and so forth. So it got split. Well, let's take a look at these hydrogens right here. Okay, we're gonna say what's the splitting of the 8A signal. So right now in my mind, that signal is one line. Okay, one signal representing what? An integral of 3. Remember integrals? So this is 3HA, but I don't know the splitting just yet. I describe these hydrogens as being mini magnets. So you do have an external magnetic field that aligns all the spins, the proton spins, either up or down. But if each hydrogen is its own mini magnet, then these protons should feel the influence of magnets that are nearby. Now, let me just give you one rule right now. Equivalent hydrogens do not split each other. Okay, so these two will not split. They're the same signal. That will make much more sense when we start analyzing more the splitting of different protons. We should write that equivalent, chemically or magnetically equivalent hydrogens, oops, don't put a comma, do not split each other. Do not split each other. Okay, memorize that. Okay, let's go back to this filling the blank. Well, look at the hydrogen, I call this the nearest neighbor. Okay, not these. These hydrogens, you could say, live all in the same house. Look at the house next door. There's one hydrogen living in that house. We're going to call that the nearest neighbor. Okay, that nearest neighbor, for any one particular molecule, its mini magnet. Remember this drawing here? We had the down arrow for the -1/2 spin, or it could be up, aligned with the field. Okay, so really, if we have 100 of these molecules, these methyl protons are feeling a slightly less magnetic field for half of the time, or half of the molecules, because this is a 50-50 proposition. And then for the other half of the molecules, this hydrogen is aligned with the magnetic field, these protons feel a slightly higher magnetic field. So there's a little perturbation. Hence, I'm going to try to draw this as cleanly as possible. We take our theoretical singlet, and because it feels a slightly bigger field and a slightly shorter, bigger field and lower field because of the influence of these mini magnets, then you split into 2. Okay, and they're kind of wide right now, but it will look like this, like a doublet. 2 close together. I'm just showing that they're split. One above and one below, because of the perturbation, because of the influence of these mini magnets. Well, it seems like if I have one neighbor, it's called the nearest neighbor, I split into 2. That is called the n+1 rule. You take the number of nearest neighbors. Now there's going to be some exceptions, okay? For this video, I'm going to show you what all the examples I show are going to be very, very clean. It will follow this rule. Number of nearest neighbors plus 1 indicates the splitting. I know we just talked about this now, but do you see the powers? Because if I see a doublet in the spectrum, I could say that that signal, the proton represented by the protons represented by that one signal, those protons have one neighbor due to the n+1 rule. So you take the doublet, well, it's n+1, n equals the number of nearest neighbors. Okay? So we are going to call this a doublet. Now you may ask, well, what about these mini magnets way over here? Do they have any influence on these hydrogens? And for splitting, they are too far. That's why we're going to emphasize the nearest neighbors. Now, you notice that if I'm worried about, what if I'm worried about HB? I have 1 HB, some type of splitting. Well, this house holds HB, and I want to know how this signal is split. Okay? Well, the trick is put your hand on the house that you are curious about, and ask yourself, where are the nearest neighbors? Who lives in the house to the left? And how many live to the house to the right? Okay, so I point to the carbon that has the hydrogen I'm interested in, and I'm figuring out how is that signal split. I have 3 neighbors to the left, and I have 2 neighbors to the right. So you look at the house directly adjacent. You look at the neighboring house. It has 1, 2, 3, 4, 5. So 5 plus 1 is 6. Again, we have a sextet. I was really hoping for something smaller like a triplet or quartet. Okay. I think you're convinced, I hope, that by having a 50-50 proposition here, 50%, that signal, half of it theoretically is split, is going to a higher ppm to the left, and one is going to the lower ppm to the right. Okay, because that's what literally this is feeling. It's feeling 2 magnetic fields. Okay, well, 2 magnetic fields in total. This plus the external is 1 magnetic field. This plus the external is the other magnetic field. Let me give you another molecule because I want to show you a triplet. Okay, if I have a triplet, what does that tell you? That tells you that you have 2 neighbors. So I'm going to go ahead and give us a methyl group here, and okay, yeah. And then I'm going to go ahead and finish this off. I am curious, again, about these A protons. So I have 3HA. I don't know it's splitting. Well, look at this. This hydrogen here, half the time it has a mini magnetic field against the external, half the time it's with the external. But we have a second hydrogen living in the same house. So half the time it's like this, going down, the other half is this. Or you can think of half the molecules, this H has an arrow down, the other half has an arrow up. Okay, so it's still 50-50 and 50-50. Okay, we will call this proton B. This is HB and HB. But let me make them different. Let's say, well, no. We'll say HB to the left and HB to the right. Okay, does that make sense? I hope that makes sense. So one combination is both of them are down. So this set of protons is feeling a magnetic field augmented or perturbed by 2 mini magnets going down. But what's the other option? The other option is one down and the second one up. Okay. But you also have this going up and this going down. Take a look at this situation right here. Do you see how they kind of cancel out? So actually, these protons are feeling just the external magnetic field when you have these 2 situations. So you could have it in 2 different ways, either the first one down and the second one up, the first one up, the second one down. And then the last combination is both up. So you are taking your single signal and you're splitting it actually into 3 populations because these 2 are identical. These cancel out and these cancel out. This happens 50% of the time if you think of percentages. 1, 2, 3, 4. Half the time it's this one of these 2. 25%, 25%. 3 situations. And the middle situation happens twice as much. That's why your triplet looks like this. The middle peak is twice as big. This is beautiful because if you see a triplet, you know, or you can guess, that it's next to a CH2 group. I'm not saying that this signal is a CH2 group. I'm saying this signal represents protons that are next to, because these are the neighbors. These are neighbors. Okay. Now let's try this. Well, no. Let's go for an example. That's our splitting. We don't need to talk yet about chemical shift to analyze this molecule here, the spectrum here. I think you're ready. I feel like you're ready. Example number 1. Propose a structure for the proton NMR spectrum below. The molecular formula is C5H12. Fantastic. Oh, good. They gave us our integrals. They didn't do the integration, or they're not doing the integration. Okay, like this. But let me just draw something representative. But they're telling us that this represents 2H, this represents 1H, and this represents 3H? Wait, that only equals up to 6, but I have 12 hydrogens. That's not the number of hydrogens, that's just the ratio. The computer doesn't know that I have 12 hydrogens per molecule. All the computer knows is that the area under here, or the area under here, is twice as much as this. The area under here is 3 times as much as this. To see how to get up to 12 protons, I gotta multiply each of these by 2. So my real proton count is 4H, I think, 2H, and 6H. Interesting. I have 6 hydrogens that are equivalent. I can't have a carbon with 6 hydrogens around it. You know what, this is a good clue? This is a good clue that I have 2 methyl groups. Not only do I have 2 methyl groups, I have 2 methyl groups that are equivalent. Not only do I know that they're equivalent, this is a triplet. So how many neighbors do you think it has? Each CH3 group has 2 neighbors. It's not a guarantee, but many times if you have 2 neighbors, that means you are next to a CH2 group. Look at the puzzle pieces that I'm identifying. I have a methyl group. I actually have 2 methyl groups. I have a CH2 group. Actually, it should be next to each of these methyl groups. So I have ethyl groups everywhere. Not everywhere, but I think I have 2 sets of ethyl groups. That takes care of 4 carbons already. I need 5. Another thing you might want to know is how many pi bonds and rings do you have? That's the degree of unsaturation. The way I do that, I don't want to give away the answer. You know an alkane is CnH2n plus 2. That is saturated. Any molecule that has 5 carbons, the most hydrogens you could put on it, the most hydrogens theoretically that 5 carbons can have is actually 2n plus 2, 12. What that means is that there are no pi bonds and no rings on this molecule. So I better not start guessing rings and pi's. Okay. Well, I have 4 carbons listed already. Oh, if it's true that these 2 methyls are equivalent, and they're both next to a CH2 group, maybe I have these 2 ethyl groups that are equivalent. That means that these 2 hydrogens are equivalent with these 2 hydrogens. And I bet that is the CH2 group that connects 2 parts. So, say I know that it's an alkane. Okay, let me pretend that I didn't do all of this work, and I guess that maybe I have this. Isn't that C5H12? Well, if you practice enough, right down here, if you practice enough, you could easily say that, well, these protons right here, A and A, I have 6. Oh, that could be it. I have 6 HA. Nope, it's not it. Put your finger on one of the houses and ask yourself, how many neighbors does your finger have? Look at the neighboring house. There's only 1 hydrogen there. if this was a molecule, your 6HA would be a doublet. It only has one neighbor. So the danger is, I know you have two sets of A's. Don't think about this as, don't try to figure out the neighbors for both of them. Just put your finger on one of them because they are equivalent, okay? Whatever you do with one is happening the same thing to the other. Put your finger on the house A, just one of them, and again, look at the house next door. How many people live in that house? Just one is a doublet. You know, this H right here, we'll call this 1HB. It's totally split. It's split by 1, 2, 3, 4, 5, 6, 7, 8. We call that a multiplet if it's way higher than 5 or 6. Okay. I'm going to stop right there because I don't have a 6H doublet. I have a 6H triplet. How about that? That is a constitutional isomer of this. Hopefully you can tell that those two are equivalent. If I flip the molecule, that methyl group would be right where this methyl group is. But can you tell the splitting? I have 6 hydrogens for A, 6HA. Again, don't try to analyze both at the same time, and actually only analyze one of them, because it's happening to the other one exactly the same way. So I'm going to point to the A protons and ask myself, how many people live in the house next to my finger? 2. 2 plus 1, there's my triplet. Okay, look at proton B. Okay, again, put your finger on proton B, or the house that has proton B. Now, do you notice that my thumb has 2 neighbors, one on the left, one on the right? How many people live in each house? 1, 2, 3, 4, 5. This is a sextet. But how many B protons do I have in total? 4. 4HB sextet. Okay. Next is the middle one, pink, C. I have 2HC. Again, put your finger on the house of C and say, literally, how many neighbors do I have? I have neighbors on the left, 1, 2. Neighbors on the right, 4. This is a pentet. 4 plus 1 is 5. Okay? Please, 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 use the finger technique because you don't want to double count a neighbor. Like, if you put your finger at A, you're not going to count these 2 hydrogens as a neighbor, even though these 2 are equivalent. Okay? Even though these 2 are equivalent. You just literally ask yourself, how many neighbors does your finger have? And you'll be fine. Okay? And there it is. Triplet, sextet, pentet. So triplet is the A protons. Sextet is that guy right there. That's the B protons. So the C protons are in the middle, right here. Okay. Alright? A, B, C. And that's what you call assignment. Alright? Now, I can't believe it's already 23 minutes. This is so much fun. Said unsarcastically. I'm not going to get to chemical shift. Because there's so much we can do, right? There's so much we could do just from the number of signals, the integrals, and the splitting. I did not need to know that a methyl group occurs around this ppm, or that CH2 groups occur around these ppms. I did not need to know that. I was able to figure out the spectrum and same you just based on splitting and the integral. Right? They taught us the integral here. Alright. I can't believe I'm not going to get to chemical shift. That will be... You know what? I don't know if I'll even make a video on chemical shift. You can learn that on your own. Just, look at some tables and you'll get a feel for chemical shifts. So for instance, a benzene ring is a chemical shift around 5.5 to 6.5. Actually, I think in this next example, we're going to talk about the vinyl proton. A proton off of the CC double bond that's not part of the ring. Okay. So let me give you one hint about a chemical shift for this particular problem. If you have a proton off of a CC double bond, that proton right there is going to be between 4.5. Let me write it in the order of how it is on the scale. 6.5 down to 4.5. Alright. Well, look at that. Those are vinyl protons. I'm almost positive they're vinyl protons. We don't have any, if you know about shifting a little bit, chemical shifts, we don't have any electronegative atoms that are pushing the signals down to the left. These are vinyl protons. So this is called a vinyl proton. It's right off of the double bond. But look how many we have. 1 and 2. Just double. Oh, we're not given a chemical formula. So we can assume that this is 1H and this is 2H. This is a guess, okay? But I'm guessing we have a double bond, but I'm also guessing that that double bond is responsible for these 3 hydrogens. How? 1, 2, 3. Okay? And then the rest of the molecule. You may ask, wait a sec. What's the splitting? What's happening with the splitting? Why is it so complicated? Yes, with pi bonds, you could have long-range splitting, and the effect of hydrogens that are far can have an effect. Right now, I'm really dependent on the integral. Okay, and also, I'm going to assume, it's an educated guess, that maybe these 2 are these 2, and then this one lone hydrogen is this one right here. Okay. Don't get hung up on trying to identify every single reason why something would be split, or how the splitting would occur, because, again, it could get complicated. A lot of times your goal is to propose a structure that fits most of the puzzle pieces, even if you don't understand, well, what is that? That doesn't... I mean, we had a really clean sextet before, right? It's pretty symmetrical, good looking, right? But this one is horrific, okay? I'm not going to even try to predict why it splits like that. But look at what's on the right. I predict that you have a CH2, CH2, and a CH3 just based off of the integrals. Okay, you know what? I'm going to guess something that's very simple. And I'm going to double check if it's correct. If not, I'm going to rearrange some atoms, okay? But I know I have, what? 2, 4, 6, 10 hydrogens. 10 hydrogens, okay? Alright, let me start actually, okay. I'm going to say these are A. I'm going to say these are B. I'm not going to worry about the splitting. The chemical shift tells me that it's way down here. Again, this is just from familiarity that the vinyl protons I know are 6.5 to 4. Okay. Let's call this, forget about the spectrum, C, D, and E. Okay? Again, forget about spectrum. You made a guess. Does your guess make sense? E. I have 3HE. Can you tell me the splitting on that? Point to the house of E. Who lives next door? 2 hydrogens. Triplet. D. I have 2HD splitting. Put your finger on the house of D, and I have a neighboring house to the left that has 2 hydrogens, one to the right that has 3. That's 5. 5 plus 1 is sextet. Do I have that? I'm not going to even look. Okay? Let me do my analysis first, and then I'll look. 2HC, finger in the middle. 1 neighbor on the left. 2 neighbors on the right. 3 plus 1 is a quartet. Our first quartet. And then already B, you know, I'm not going to worry about the splitting because it looks horrendous. But the integral works, 1HB. And 2HA for this one right here. You see that? I'm not worried about the splitting. you know, on an exam, if I could match like 90% of the spectrum, I feel I'm good to go. 3H triplet, 3H triplet. 2H sextet. It's this one right here. That's 6. You could tell it's an even number because the two middle peaks are equal height. Sextet. Quartet. 4 is an even number. The two middle are even height. 1, 2, 3, 4. Okay. Can I even attempt to talk about the splitting here? Look at B. Okay. B is right here. Because it has two neighbors on the right. Honestly, these two HAs are slightly different, right? Because this HA is always closer to C because this bond is locked. Okay. So I'm not going to get into this. This is beyond the scope of this video. But yeah, the splitting for B would be pretty complicated. And the splitting for A, kind of complicated. You know what's happening here? Because these two HAs are slightly different due to the rigidity of the double bond. Okay, the one going down is always closer to this carbon, right? This hydrogen going down is always closer to this C than this hydrogen going up. So these two are technically different, and they're overlapping. This is really a 1H situation, and they are actually splitting each other also. That's why it's more complicated than what you would predict. I'm sorry, I have not gotten to chemical shift, but we were able to identify two molecules for two spectrum by just knowing the number of signals, the splitting, and what? Oh, the integral. Just those three things. Okay. All right. I don't know if I'm going to put up a video for chemical shift. I may. I do have a study sheet that tells you some very important chemical shifts, okay, especially for the methyl groups and the CH2 groups when you're next to an oxygen. Those you'll pick up as you do more practice. Okay. Maybe I'll make this available as well. It's a little study sheet. Whew. NMR.